All right, guys, lesson 3.1 here, talking about area, squares, and square roots. We're going to interpret and simplify the square of a number and then determine the square root. All right, so let's jump right into it. So Dominique Wilkins, anyone know who that is? Good basketball player back in the day. Did some dunk contests against Michael Jordan and stuff like that back in the 80s and early 90s. Anyways, the school's holding its annual school carnival, right? Each year, classes and clubs build game booths in the school gym. This year, the student council has asked Janelle's math class for help in deciding what size booths should be and how they should be arranged. So the class will begin this work by reviewing some ideas about area. All right, so let's take a look. Example A here, we want to find the area of a rectangle, okay? And the rectangle has been divided up into squares. So the rectangle itself is the whole big figure, right? All this entire thing. And we want to talk about the area. So to find the area of a rectangle, right, we should be familiar with the formula. Area of a rectangle is going to be the length times the width. So in this case, the rectangle we can kind of count is 1, 2, 3, 4, 5. So the length is 5, and then the width is 3. Okay, so 5 times 3, of course, is 15. Now just keep in mind, if these are each centimeters, okay, if you do 5 centimeters times 3 centimeters, the answer is not just 15 centimeters, it's actually 15 centimeters squared, okay, or squared centimeters. And if you count up the total number here, right, there's 3 rows of 5, okay, or 5 rows of 3, depending on which way you're looking at it. Either way, you have 15 squares, okay? So note that the units are centimeters squared, and this represents the amount of surface that this rectangle would cover, okay? All right, so let's take a look down here. Before deciding how to arrange the booths, student council needs to know the area. Several class members went to the gym to measure their floor. So they found that the gym floor was 84 feet. That was the length. And the width was 50 feet. Okay, let's find the area of the floor. So again, area of a rectangle is just the length times the width. So in this case, 84 times 50 is 4,200. And again, we're going to do feet. We're going to put that little exponent up there. Okay, we'll talk about that more in a second, but that's just to say that it's square feet, because remember, there would be a whole bunch of little squares in here. I'm not going to be able to draw nearly as 84 of these rows and not 50 columns, but you get the point. There would be a whole bunch of them. There would be there would be exactly 4,200 square feet, okay? And that's the amount of surface covered. Oops. Okay, if you think about little tiles or little blocks, there would be 4,200 1-foot squares inside that gym. 4,200 square feet. All right, so what do we got now? So the class is going to focus on the area of squares, right? Because this is the shape of the base of many of the game booths, okay? So not necessarily a rectangle, right? In a rectangle, the length and width may be different values, right? A rectangle has a length and a width, while in a square, all 4 sides are equal. Okay, so a square is just like a special kind of a rectangle. So if we look at example B here, do we need to know both the length and width? You don't have to be given both, right? Because again, if it's a square and they give you one side, we know in a square all 4 sides are equal, or congruent is the fancy word. So I know that every single side is going to be 4 centimeters. So in this case, if one side is 4, that's all we need. Multiply it by itself, right? You still do a length times a width to get an area. It just happens to be both numbers are the same. So the area of this square would be 16 square centimeters. Okay, let's try this. Let's look at look at a table here and get some values filled in and just kind of really dig into what's going on. So the drawing here shows the floor, right? It's a square. They're going to use a variable s. Okay, it could be any value. Okay, s in the previous example was 4. Okay, or s is for side length. S could be 4. S could be 10. S could be 6. Okay, it could be anything, and that's what a variable is used for a variable, if you think something that varies, is something that's changeable, right? So this s here is just kind of marking as a side length, but it's not a locked-in value. In the table here, we're going to see a lot of different values for s over here, right? And let's see what happens. So let's complete this table by finding the areas of some different size booths. The length of a side in feet is represented by s, right, as in the drawing above. Let's include units for area in the last column. So if in the top row there, s equaled 3, to get the area, it's just going to be 3 for the length times 3 for the width. So 3 times 3 gets us 9 square feet. If s were 6, if it's a square, the area is going to be 6 times 6, which of course is 36 feet squared. Okay, if the side length was 8, the area would be 8 times 8, which would be 64 square feet. If s was 11, the calculation would be 11 times 11, which is 121 square feet. Okay, 4.2, digging out my calculator here. 4.2 times 4.2. Oops. Uh-oh, there it is. Sorry, I got a little sloppy in there. Calculator tells me it's 17.64 square feet. And lastly, 10.5. 10.5 times 10.5 should be a little over 100, right? Let's see what we got. 110.25. And again, area is always a squared unit, so square feet. All right, so area of a square is just like a special rectangle. The length and width are equal, so it's a number times itself. Okay, so that leads us into a kind of a big concept here. That's what we just did. We found the product of a number times itself, right? I just said that. It can be written as a power, okay, with a base and an exponent. So let's take a look at that. Let's see what this means. So example C here. If we want to write 5 times 5 as a power with a base and an exponent. So the base is going to be 5. Okay, it's really, here's the format. It's kind of like you have a base raised to a power, okay, or exponent, sometimes they're called. And what it is a shortcut way to write a number times itself a certain number of times. Okay, so this is what it looks like right here for that example. 5 times 5 could be written as 5, and then you have a little a superscript. Okay, so a subscript is when you write a number smaller, but it's lower than the number. A superscript is when you write a smaller number kind of above the number. So this is read. It's read as 5 to the second power. Okay, it's an exponent. It's an exponential form. Let's look at a few examples, and we'll talk about in a minute why it would be helpful. Okay, so if we wanted to write 12 times 12 in exponential form, right? So the base, the thing we're multiplying is 12, and it's getting multiplied by itself a total of 2 times. Okay, 1/3 times 1/3. I'm going to throw it in parentheses just because it's a fraction. But the base is 1/3. It's getting multiplied by itself a total of twice. Okay, same thing with this one, 3.25 to the second power. Okay, it means times itself. So notice it is not saying, like for instance, this first one here is not saying 12 times 2. Right? It is 12 times 12. It's 144. Right? 12 times 2 is 24. So this is a lot different, and sometimes when you get going too fast, people accidentally just multiply 12 times 2, but it's really 12 to the second power. Okay, and let's take a look. Let's look at the next problem down here and see if we can use it. So the table below gives some booth sizes in exponential form. Let's copy and complete the table. Okay, so this will be a good practice for us. So the top row is done. 5 to the second power, we know that equals 5 times 5. Standard form value of that's 25. Okay, the next row, 2 to the second power. So the base is 2, and it's getting multiplied by itself, a total of twice, equals 4. Okay, what about 1 to the second power? The base is 1 times itself a total of 2 times. Okay, 7 to the second power, 7 times itself. What about 15 to the second power? 15 times 15. Anyone know without a calculator? 225. Okay, so it's a shortcut. And the cool thing is, let me just slide down a little bit. It can really save you some work. Like just as on a side note here, this section's all about just having the exponent be 2. But if you had something like 3 times 3 times 3 times 3 times 3 times 3 or something, you can make the exponent as big as you want. Okay, that would be equivalent to, how many do we have there? 1, 2, 3, 4, 5, 6. So this thing right here would be equivalent to 3 as the base to the 6th power. Okay, because there are 6 factors of 3. You're multiplying 3 by itself 6 times. And just for the sake of example, that actually equals 729. That would be the standard form on that. All right, so let's keep working here. So let's say, let's kind of dig in a little bit and kind of even go backwards on this. So if the area of the floor of a square booth is 36 feet, what is the length of the sides? Right, so they're giving you the area. They're kind of giving you the answer. So step 1, so the area is the square of the length of a side. So 36 feet squared is the square of S. How do we undo that, right? I don't want to do 36 times 36. Okay, because 36 is already the answer. We want to figure out what was the length of a side. So there's a special symbol that is called a square root symbol that you see right here, okay, or a radical symbol, sometimes they call it. And to solve that, you need to think to yourself, what number times itself equals 36? Okay, so of course the answer is 6, because 6 times 6 equals 36. Let's see if we can answer a few more. Try these. D, right? Find each square root. What is the square root of 16? Well, I know that 4 times 4 equals 16. So the square root of 16 is 4. Okay, 81 is 9 times 9. 100 is 10 times 10. Okay, those are the square roots of those values. You'll want to get used to, or kind of just familiarize yourself with the first 10 or so. These numbers are called perfect squares. Now, for example, the square root of 16, right? I expect you guys to know that equals 4. But the square root of 17, it's not a perfect square. It's not a whole number. That one, I mean, we should be able to realize it's just a slightly bigger than 4, but you would have to get a calculator to really get it more exact. Okay, so just focus on knowing the ones that are whole numbers, and those again are called perfect squares. All right, so let's look at this table down here then. So the carnival booth sizes are assigned according to the number of members. So in this table here, the first row, 1 through 30 members, they want the area of the square booth's floor to be 36 feet. So how long would the side length need to be? Right, if the area is 36, the side length would need to be 6 feet. All right, then in the next step here, we have, if there's 31 to 60 members, they're telling us that the side length of the booth floor is 8, and it's the area that we need to fill in. Right, so if each side is 8, what's the total area? 8 times 8, 64 square feet. Okay, if there's more members, right, 61 through 90, we need a bigger area. If each side is 9 feet, that would make the area 81 feet squared. All right, and then even bigger yet, 91 to 120. If the area is 121, so the area is 121, right? So what would the side length be? So we got to think about, if here's the square, 121 is there. What is each individual side? That's the new concept. That is, we're going to take the square root of 121. Okay, there are buttons on calculators that do this stuff. Now again, I would encourage you to know up through 100. There are 10 perfect squares. But once you get a little higher than that, you might know a little bit more, but as you do them, you'll kind of recognize the first 10 or 12, like I said. But the square root of 121 is 11, okay? And you can check that. 11 times 11 is 121. And then if the area was 144, I know that 12 times 12 is 144, okay? We can use that concept, okay, the last thing in this section, to solve equations. Okay, look at example E. They want you to solve the equation s squared equals 36. Okay, that's kind of what we were just doing. They're giving us s squared. They're giving you the area. Okay, so if you think about, if you have an equation, so let me get a pen here and just write this a little larger. S squared equals 36. And you want to figure out what is s, right? You just want regular old s. So it's just like anything else. When you solve equations, you try to isolate the variable, get it by itself. In this case, the way to get rid of that exponent or that power is to take the square root of both sides. Okay, square rooting is the inverse, okay, of squaring. Just like adding is the inverse of subtracting. Like, it undoes it. So that's why when you take the square root of s squared, the square root symbol out here makes the exponent cancel out, and that's how you get just s. And then the square root of 36, what times itself equals 36? The answer is 6. Okay, so the assignment for you guys will be in the book here. It's on page 37, and we're going to do numbers 9 through 14.